So we've been using advection quite a bit in the last tutorials, but let's look what actually happens when we're advecting points. So let's look at this slice through a volume here, through a vector volume. And each of these given voxels contains a vector pointing in a given direction. So in our case, this would visualize as this if we draw each vector as an arrow. So for example, let's try advecting this point down here. So the first move it would make is this, because our vector in this voxel, where our point is, would point in this direction. So after we've moved our point over here, we do the same thing again and look up the vector pointing in the new direction from this voxel and moving the point along. So we'd end up here. So in the end, after we traveled through this whole volume, our point would be here and have traveled this path. And that's all there is to point advection. So what we could do, for example, is build a setup like this using point advection. And I really like it because it combines the aesthetics of wires with the aesthetics of a Voronoi pattern. To build it, we start with dropping down a grid, diving in there, and resizing this grid to be 3 by 3 in size. Then drop down a scatter, and we're going to scatter 120 points. Next we're going to copy some spheres on those points we just created. Whoops, that is the wrong slot, and we need to create a sphere to go into the other slot, like so. And I'm going to dial down the sphere radius to 0.2, then highlight the copy to point sub. And also I want to set up my sphere to be a polygon and increase the polygon frequency like this. Maybe that's a bit too much, like this. Also, I don't want these spheres to be uniform in scale, so let's drop down an attribute randomize in order to create and randomize an attribute called pscale. That is only one dimensional, it's just one float, and let's tell it to be random between 0.1 and 0.6. Wire this up, that looks good. Next, what I'd like to do is, out of those spheres, create an SDF VDB. And the SDF VDB that I'd like to create should have a rather huge padding in order to be able to advect points through it. And as you know, VDBs usually are sparse, so when advecting points away from those spheres, they would not get really far because soon the VDB would end. So let's create a VDB with the VDB from polygon sub here, wire this up in here, highlight it, and this is a bit too coarse. So let's lower down our voxel size to something rather small, like this. And in order to create a VDB where we can advect points through, let's on the one hand fill the interior voxels of that geometry, of that SDF that is, and let's crank up the exterior band voxels really high to something like 128. And you see now Houdini takes a while to calculate this because there are lots of voxels in this volume. Next, in order to create a vector field where we can advect points through, we're going to use the VDB analysis and turn our SDF here into a gradient here, so that will give us the basic vectors along which we'll advect the points. However, I would like to do a neat trick. Drop down a volume VOP again, and as in one of our previous setups, wire in both the SDF in the second slot and the gradient in the first slot. And in the volume VOP, let's drop down a multiply node and a volume sample to read in the SDF, and a volume sample vector to read in the gradient vector. So gradient comes in through input 1. We want to sample it on the current voxel position, that's P. The SDF comes in through input 2, and we also want to sample it on the current position. And all I'm going to do now is multiply those two values. So the direction of our vectors is given by the gradient, so it's pointing away from the surface, and the magnitude, that is the length of the vector, is given by the distance from the surface. So let's delete that volume output here and instead first make sure we have our volume properly named, which we don't. So let's give this a custom name and call it vel for velocity in our case. And in here, attach a bind export and set it up to export velocity. And that is a vector, like so. Takes a while to calculate. And there it is. Okay, let's advect something through this volume. And just for test reasons, let's drop down another grid. Scale it to be 3 by 3 as well. And first drop down the volume trail, because what the volume trail is doing is it's advecting points which we feed it and automatically generating a trail out of them, so it's very good at visualizing vector volumes. We can see something weird is happening here. Let's increase the rows and columns number here, so that we can actually see something like this. And we see several weird things. On the one hand, we're getting this Voronoi-ish pattern. That is because in the regions where 2 points have the same difference from each other, the direction of the gradient has nowhere to go. So we're getting these advection errors here, where the point is trying to find a way between all those voxels in here, and that's yielding those patterns. On the other hand, we're also getting these upward patterns here on the corners where 3 or more edges meet. And currently my speculation is that this is down to numerical errors in the advection procedures, or sampling errors, because compared to these small areas, our voxel size is pretty big. But it's something we can work with. The only thing that I don't like is that these trails go off not only upwards but downwards as well. So let's fix that by first disabling auto update to manual, so I can work within this volume bob without Houdini constantly trying to update my viewport and thus slowing down. And now, I really like what's happening with the advection on the X and Z plane. However, I'm not sure about these Y values becoming negative here. So let's take care of this by first attaching a vector to float to get the individual components of our vectors, and then an absolute value. So we will take the Y value and feed this in there. This will take care of these negative values turning positive. And last but not least, we would like to turn this into a vector again with a float to vector, where we wire in the absolute Y in here, and the X in here, and the Z in here. And let's wire that to the out. Okay, let's enable updating again. Takes a while to cook. And we see now we have all those trails pointing upwards. Perfect. Okay, instead of this grid here, let's advect something more interesting and use the same copy to points. But this time, let's not copy the spheres, but let's create a circle. Make this circle a little bit bigger than this sphere. So this sphere has a radius of 0.2. Let's give this a radius of 0.21. So we start with our advection on the outside and not exactly on the sphere, because exactly on the sphere the SDF would be 0, and thus no advection would happen, because I would scale the gradient by 0, so our points wouldn't go anywhere. Also set this circle up to have its orientation in the ZX plane, set it up to be a polygon, and maybe have 64 points. Visualize this like so, and feed this into the volume trail. Highlight our volume trail, and we see now we have those circular patterns where our trails emit from. That is going somewhere. To give this a bit more detail, let's use that same copy sub again and create another sphere. Again, polygon, maybe 8 divisions here. Let's dial its radius down really small. And also just copy this onto the center of our spheres. And merge this with our volume trail, like this. Also, it would be nice to have some small spheres on the original points of our point advection. So let's use the points that come out of here in another, in another copy to points, like so. Highlight this, and there's lots of points feeding in there. And I think we can dial down the frequency of that sphere here, so it gets a bit quicker. And also we can dial down the sphere radius a bit. Like so, and merge this as well. So we now get this. Let's clean up our setup a bit, if that's possible at all. Yeah, maybe something like this. And let's say we want to have this animate. So instead of the volume trail here, let's drop down a BDB advect points. And pretty similar to a volume trail, this needs on the one hand the points, on the other hand the velocity volume in here. Let's highlight this, and let's see what happens if I hit play. Nothing. That is because currently I haven't specified a velocity VDB, so let's do that by telling the VDB advect points to use the volume called vel to advect the points. So I'm going to drop down at name equals vel, like this. Let's try again. Still nothing. What did I miss? Oh yeah, of course. On the one hand, what I did here is delete everything but the points. So we're only advecting points and not the polygon. On the other hand, of course, I need to drop this into a solver, so it moves. And this solver is going to take in the points on the one hand and the VDB on the other hand. And this is going in there. Wire up the incoming points and the incoming VDB. Still highlight it, highlight the solver, and hit play again. And we see now we have advection going. Let's say we want these points to leave a trail. Thankfully, there's the trail sub. It's not the fastest sub there is, but for our case, it's simple enough. And the setup is still reasonably fast even when using it. So I'm going to set it up to have a trail length of 240. Hit play again. Well, as I said, not the fastest sub in the world. So let's cook. Let's jump to the end. We can see we're here at a stage where these movements in the y-axis just start to happen. So let's increase our timeline to go to 480 frames. and jump to the end there. Oh, and we also need to increase the trail length, of course, to 480. Like so. Also, I could set up my trail to generate splines by setting it to connect as polygons and uncheck close rows. And now we have these animating splines that yield these beautifully abstract structures.